Yeah. Let us start to go for the class now. Don't be crazy about your attendance. This subject is supposed to be the most critical subject in your whole syllabus. So try to be attentive and go through the books if it is available with you. I can't give you from the library because you are not allowed to come in. Books should be L.S. Srinath. That is the best thing I have got. We'll follow that book and try to do it regularly because we have to put a lot of effort to understand this subject. This is supposed to be the most critical and difficult subject in your whole syllabus up to the fourth semester. Okay, let us start. In the last class, I have started talking about the Morse cycle. I am repeating it. That's why, because I am trying to explain it again and again because it is extremely critical subject, especially this chapter of analysis of stress. This is extremely critical and difficult subject. And after going on, I will repeat this chapter again because you have to clear it for this for this subject concern. Next of the chapters are not that difficult, but this is the most critical subject. Actually, I am supposed to teach it after the strain, but I have started the stress just to give you an idea. After I completed the strain, I will repeat it again, and definitely that will go. I will do it much quicker, but I will repeat because others are simple. Okay, let us do it. In your strength of material classes, in 2 years back, we have gone through the Morse cycle. Morse cycle is like a conception behind the Morse cycle is like this. If we have a particular prismatic bar subjected to a force along x-axis, along y-axis, and subjected to shear, this force may be tensile, may be compressive, and subjected to shear stress along x-axis, along y-x-axis. When what will be the principal stress over a plane subjected to an angle, say theta, with the longitudinal axis? And first, what is the normal stress acting over a plane which is subjected to an angle theta with the longitudinal axis? Next, what is the maximum value or what is the principal value of this stress? And what is the optimum plane over which this principal stress is acting? Principal stresses are principal tensile and principal shear stress. It is assumed in your undergraduate in your strength of material class. It is proved that a plane subjected to principal stress or maximum stresses, or a plane subjected to principal stress or minimum stresses, don't have any shear stress acting over it. But maximum shear stress also acting over certain plane, and over on that plane, it is principal stress is not normal stress is not exactly zero. Next, what is the benefit of this Morse cycle is in your analytical cases you have to go through all the calculations, and but in Morse cycle if you plot your input incoming stresses given to you over this axis, you can safely plot the maximum shear, maximum principal stress, or the stresses on any plane from the by measuring the respective dimensions on the Morse cycle itself. This gives you fairly accurate result. May not be that accurate in analytical cases, but more or less equal to the analytical value. And this is a quick and easily accepted process which is established in Morse cycle itself. Now, as I have told you time and again, we are interested to know what is the condition of stress over an plane. We are not interested to know what is the condition of stress over a plane, but we are interested to know what is the stress over a point, which is in space, especially what is the maximum stress act going through that point, what is the minimum, and if there exists any in between, what is the in between stress going through that point. Maximum, in between, and minimum stress, and otherwise called major, minor, and in between stresses, or simply principal stresses. There are three principal stresses: sigma x, sigma 1, 2, 3, because 1 is maximum, 3 is minimum, and 2 is the intermediate. This is the more or less accepted practice. Uh, Now, how we are doing, how we are making the principal stress in a geometrical plane when when the stresses are going through a certain point only, not through against a plane, like our strength of potential discussions. What we do here is, let us discuss a geometrical construction that brings out some important result. It is a geometrical construction. You have to draw as per a certain scale, and you have to establish, or you have to find the scale by your own shape, which is convenient for you. Say, according to the size of your paper, have answer script or like this. It should not be too big, and it should be too small, like I have done it here. It is too small for the stress itself, but it will still, it can give you serve your purpose exactly. Now, then again we are thinking of a point. Say the point is P, it is any point which is in space, and let the frame of reference P X Y Z is drawn through this point. Frame of reference means we always take this name. This is the name of the reference plane, OX, OY, and OZ, three mutually perpendicular planes. The origin is O, and OX is along x-axis, OY is along y-axis. Generally, it is the vertical axis, and OZ is another horizontal axis, but it can be different. Okay, but here we are putting this frame of reference OXYZ from through the point P, means PXYZ. And what we are doing is, we are plotting the principal stress axis along x, y, and z. So initially, we are getting a point. We are finding dropping the principal stress on the point two three mutually perpendicular axes. So x, px, pi on pz. Now, as I have told you a number of times, through any point, infinite number of planes can be drawn, and each plane can be defined by means of the normal acting about the plane, or each normal can be defined by the name of the plane over which it is normal to it. Now here, let us assume a plane with normal n acting through the point P. Through the point P, we have three principal stresses along OX, OX, OY, and OZ. And through the point P, we have a plane who has a normal n starting from the point P itself. Now, let sigma be the normal stress, and tau is the shear stress acting at this point. There are principal stresses resulting from which from a sigma normal stress is sigma, and shear stress is tau. And we are assuming this is acting through this point, these two sigma and tau acting through this point. First, finished. Next, we are looking for another axis for sigma and tau, as there is only two equations, only two items. One is normal stress, one is shear stress. We can safely plot it in a two-dimensional axis where O is the origin, and horizontal axis is going throughout like this, from O to rightwards and O to leftwards, and OY is the tau axis or vertical axis, originated from O and going upwards as positive direction, and originated from going to O going downwards for negative direction. O positive direction along sigma axis will be rightwards, and O positive direction of the signal axis will be leftwise. So here, from the point P, we are through the point P, we are having this stress, normal stress sigma, and normal stress tau, and we have the normal n, which is coming out through the, which is the normal to the plane going through the point P itself. So, and there are two confusions here maybe you may face. First of all, I am telling there is the axis O, P, X, Y, Z. This is the coordinate plane. P is the origin, not exactly O. And we have the normal stresses in three components: maximum, minimum, and intermediate in along the three axes itself. Next, we are imagining another plane which is going through the point P and who has a normal N. And this point P through which one shear stress, one normal stress is acting, which is sigma, and through point P, another shear stress is acting, which is tau. Now, what we are doing, we cannot draw anything on three-dimensional plane because we don't have it other than CAD. In a piece of paper, you can draw only a two-dimensional axis. So here we are drawing only two-dimensional O2 sigma x-axis along the x-axis, so-called x-axis, where it is positive from O2 rightwards and negative from O2 leftwards, and tau O2 O2 tau, which is the along y-axis, which is positive from 0 to upwards and negative from 0 to downwards. Now, now we can mark a point Q over here, say here, any point over the plane with coordinates sigma and tau. This point have a coordinates in two dimensional, not in three dimension. In x along 0 sigma axis, it has a coordinate, it has a value equal to sigma, and 0 tau axis, it has a value equal to tau. So we have a two-dimensional plane, 0 sigma, O sigma, and O tau, and any point over it will have the coordinates sigma and tau according to the position itself. Now, and we can say that the normal, this sigma and tau represent the value of the normal and shear stress on the plane N, which I've just told you passing through the point P, and this sigma and tau is the stress on that plane acting over the plane itself. One is normal, that is sigma, tau is the shear or along, that is equal to tau. And we can have a lot of different planes passing through the points, either this plane or that plane. An infinite number of different planes can pass through this point. And we got always supposed to get different values on tau and sigma because the plane is different and axis is also, reference axis is also different itself. Now, for any plane, a point can be located with coordinates sigma and tau. For the same reasoning, for any plane, we have this point, and its value in coordinates is known to us. Now, plane with the sigma axis and tau axis called shear planes pi, with sigma axis and tau axis the plane. So far, we have talked about the normal to the point. Now we have talked about the plane which is carrying the sigma axis, sigma, and the plane which is carrying the tau axis. This is called stress plane pi, but it is not 3.14, just the name itself, and nothing more than that. The shear plane pi. The problem is now is to determine the bounds of tau, sigma, and for all possible values of for possible direction of n. Now we have to say, find out what is the value max, what is the bounds, what is the limit of q, how much we can, where we can plot the q, whether from 0 to infinity or any other specific places. So we have to check it that analytically and as well as graphically itself. So we have to find out the bounds for q and sigma and c for all possible direction n. Now, let us arrange the principal stresses, which is supposed to be known to us along algebraically, and it has value sigma 1, sigma 2, and sigma 3. We are assuming they cannot be equal to each other, or they are, for the time being, they are not equal. There are other instances I will go afterwards. If you have become time today, they are somehow equal, somewhat they are not equal. But here we are saying sigma 1 is the maximum, sigma 2 is the in between, and sigma 3 is the minimum itself. Now, along the x-axis, first of all, mark the sigma. How will you do? This is the origin O. This is not, but this one, this is the origin O. We are marking sigma 1 from here up to the point A. Sketch is not clear by me, but it is extremely clear in the books. You have no confusion about it. But from 0 to A, we plot the value of sigma along sigma axis, O to sigma axis. From 0 to B, we got plot sigma 2, again along the positive direction of sigma axis itself. And from 0 to C, we plot the value of sigma 3, which is at the negative direction of sigma axis. So we are plotting 2 sigma on the highest intermediate along x-axis in the positive direction and the minimum along the negative direction. Okay, this is positive, this is intermediate, and this is negative. So we have got 3 points A, B, and C all along x-axis or all along O sigma axis itself. So this point A, B, C represent 3 principal stresses, and associated shear stresses are 0 because all these 3 points exactly on the 0 sigma axis, because and on the axis of sigma, 0 sigma axis, there is no shear stress because along y-axis or 0 tau axis, it is equal to 0 because it is all 3 are acting over the x-axis or sigma axis itself. So here all associated shear stresses are 0. So what will be the maximum value of shear stress? Is half sigma 1 and minus sigma 2, and the associated normal stress is half sigma 1 plus sigma 3. This is indicated by the point D in the outer circle. The maximum value of sigma, it can be what is the maximum shear stress? It is the diameter D here over a circle which is being formed with the diameter sigma 1 minus sigma 3, which means as sigma 3 is negative, so this will become sigma 1 plus sigma 3. So full diameter is from here to here, and radius is sigma 1 minus sigma 3 divided by 2, which is the radius, which is equal to the value of the shear stress from x-axis to the from sigma axis to the tau axis. So this is the value of shear stress itself. This is the maximum value of shear stress over the plane itself. And according to the maximum value of shear stress, we know there exists a principal or normal stresses. Normal stress is not 0 here. So we have to find out the coordinates of D itself. The y coordinates of D is sigma 1 minus sigma 2 divided by 2, and x coordinate of D will give you the normal stress we need, that is sigma 1 plus sigma 2 divided by 2, which is the point here coming from here. Here you will eliminate sigma 3 from sigma 1. Sigma 1 minus sigma 3 means sigma 1 plus sigma 3 in value, and sigma 1 plus sigma 3 means sigma 1 minus sigma 3 in value, and divided by 2 will come more or less here, or equal to the, which is equal to the radius of this particular cycle. Okay, that will be the x value or normal value of shear stress here. Now, there are 3 maximum values of shear stresses, just I have told you. There are 3 maximum values of shear stress, maximum principal stress, sigma 1, sigma 2, and sigma 3 for normal stresses. Or then there are 3 maximum values of shear stress is possible. These are being sigma 1 minus sigma 3, which I have told you, sigma 2 minus sigma 3, which is the next one, which is the radius of the circle accordingly, and sigma 1 minus sigma 2, it is the radius of another circle, sigma 2, which is the radius of another circle, which is it will be like this. First is sigma 1 minus sigma 3 by 2, which I've just told you. sigma 1 minus sigma 3 means sigma 1 plus sigma 3, because minus is negative, sigma 3 is negative. So sigma 1 plus sigma 3 divided by 2 is the radius from here to here. So this is the biggest circle here. And sigma uh, sigma 1, sigma 2 minus sigma 3, this is sigma 2 at the point B, and sigma 3 at the point B, at the point C. Here sigma 3 is negative, so actually this is sigma 2 plus sigma 3 divided by 2. It is the diameter from C to B, and the shear stress there will be equal to the radius itself, or equal to the value of sigma 2 somewhere here, say E, but not over the O sigma line. That is the diameter radius of this value cycle, which is given equal to sigma 2 minus sigma 3 divided by 2. Okay, and the stress, normal stress correspondingly will be according to that sigma 2 minus sigma 2 plus sigma 3 minus 2, actually sigma 2 minus sigma 3 divided by 2 itself will give you the sigma value of sigma along the y-axis itself. And third, which is sigma 1 minus sigma 2, that is sigma 1, this is sigma 2. So the radius, the diameter will be sigma 1 minus sigma 2 divided by the sigma 1 minus sigma 2, and the radius will be sigma 1 minus sigma 2 divided by 2. And this is the value of the radius of the cycle, which is equal to the value of the shear stress over this cycle itself. And the ordinate, which is sigma 1 plus sigma 2 by 2, will be given by this, by the x-axis or abscissa of this point itself. So we have abscissa, we have the x sigma and tau value over all three different planes. One is the outermost, one is the intermediate, one is the smaller one. And there are these points are available either on this circle, or on this cycle, or on this cycle itself. But the point Q, which is not over any other of the cycle, but in between T, in between the uncommon space between the circle itself. Let's go to the next step. Stop share. Just 1 second.
सर
Yeah.
मतलब कि जो तीनों प्लेन में, मतलब कि तीनों सर्कल में किसी में नहीं है, वही पाई प्लेन है।
हाँ, क्या था?
सर के जो है सर सिग्मा 1 सिग्मा 2 सिग्मा 3 सर।
हाँ, ठीक बोलते
तो जो पाई प्लेन है सर, वो तीनों में किसी सर्कल में नहीं है, मतलब
ना what is the three cycle? What are the three cycle? How it is decided? First comes from the principal stresses, ठीक है? Three value of the principal stresses, or those are all normal, and there is no shear stresses when when we have principal normal stresses over a plane. On the plane, there exists no shear stress itself. ठीक है? So we are plotting the value of the respective stresses, one sigma tau axis or xy axis on two-dimensional plane, because on a piece of paper we cannot do anything more than two-dimensional plane itself. We cannot draw three-dimensional. So you have to follow this process like this. You plotted the value of sigma 1, 2, and 3. Sigma 1 is the maximum, sigma 2 in between, and sigma 3 is the minimum. Sigma 1 and sigma 2 has positive value because it is right side of the x-axis, right side of the origin along sigma axis, and sigma 3 is minimum and negative or compressive in nature, which is acting on the left side or negative side of the x-axis. Okay? Next, we have the points A, B, and C. Next, we draw the circle where sigma radius with sigma radius sigma 1 minus sigma 3 divided by 2. means sigma 1 here, sigma 3 is negative, so we are supposed to add the value. So total value is from here to here. This is the diameter, and for half of the diameter we bought the circle itself. And here any point over this circle, edge of the circle, not in between, where the value of the shear stress is the maximum value here on the topmost point, which is equal to radius of the cycle itself, sigma 1 minus sigma 3 divided by 2. And we have to calculate the value of, say, abscissa here, which is actually sigma 1 plus sigma 2 divided by 2, in fact normal, as sigma 3 is negative, sigma 1 minus sigma 3 divided by 2. That is the way we are plotting all three axes, three circles. Instead of our strength of material, where we are getting only one circle, here we are plotting three circles of three different conditions: sigma 1 minus sigma 2, sigma 2 minus sigma 3, and sigma 2 3 minus sigma 1, or so. And because we have a condition sigma 1 greater than sigma 2, greater than or equal to sigma 2, or sigma 2 greater than equal to sigma 3. So it may possible sigma 1 is equal to either equal to sigma 2 or greater than that. Sigma 2 may be either equal to sigma 3 or greater than that. This is the condition over which we are acting over this thing. We have plotted this cycle, and what we are saying that anywhere here, any point whose sigma and tau, any point whose sigma and tau is measurable here, is measurable from the cycle itself. Let us go through the next page. Now, everywhere, for every circle, we are having shear stresses. For every circle, we are having shear stresses and maximum shear stresses, which is the radius of the concerned circle itself. And maximum shear stress is called principal shear stress over this particular plane itself. And while the planes on which principal normal stress acting are free of stresses, the principal shear stress are not free of normal stresses, which you have just noticed. Principal shear normal stresses are all along x-axis or all along O sigma axis. So there is no shear stress over these points, but principal shear stress are along the radius, and every radius have a coordinate from O. So that is the principal. That is the normal stress acting over the principal shear stress itself. So I've just told you again, the normal stresses associated with the principal stresses are subject respectively are sigma 1 plus sigma 2 divided by 2, and sigma 2 plus sigma 3 divided by 2, and sigma 1 plus sigma 2 divided by 2. This is the principal stresses, normal stress associated with principal shear stresses. Okay? These are indicated by D, E, F. 3 points are given on 3 different circles. And it will be shown afterwards that principal shear stresses are on 45 degree to the max principal normal planes. So there is an orientation, it will be around 45 degree. The principal stress, somehow we have told that it is tau 1, tau 2, tau 3. Whereas tau 3, it was originally sigma 1 minus sigma 2 divided by 2, or 2 tau 3 is equal to sigma 1 and sigma 2. Similarly, 2 tau 2, sigma 1 minus sigma 3, 2 tau 1, sigma 2 minus sigma 3. We've just proved and shown in the practical itself. Next, we have comes the situations. We have told that sigma 1 may be either greater than or equal to sigma 2, and sigma 2 can be either greater than or equal to sigma 3. Let us consider a case where sigma 1, we have, in the last what we have discussed so far, sigma 1 is always greater than sigma 2, and sigma 2 is always greater than sigma 3. Now we are considering this condition where sigma 1 is equal to sigma 3, 2, but sigma 2 not equal but higher than sigma 3 itself. Another case is there, sigma 1 not equal to sigma 2, and sigma 2 is higher than sigma 2, and but sigma 2 is equal to sigma 3. So what will be the 3 cycles reduces to only 1 cycle, because and the shear stress on any plane will not exceed half sigma 1 minus sigma 3 in the first case, and half sigma 1 minus sigma 2 in the second case itself, because other circles will all these shear stress as sigma 2 minus sigma 3 is equal to 0. If same, they are equal to 0. If their difference is equal to 0, there is no radius for that. So we both the cases will have only one cycle each, and which have that radius equal to half sigma 1 minus sigma 2, or maximum shear stress equal to half sigma 1 minus sigma 2 and uh, half sigma 2 minus sigma 3, according to as sigma 1 is equal to sigma 2 and sigma 2 and sigma 3. There is a single cycle exists over which this has value of shear stress itself. Another case scenario is we have told that sigma 1 is greater than equal to sigma 2 and sigma 2 is greater than equal to sigma 3. The third case can be like this, when sigma 1 equal to sigma 2 and sigma 2 is equal to sigma 3. They, all of them are equal. Then when the three cycles collapse to a single side point on sigma axis, because all the ordinate abscissa or abscissa are equal, and they are equal to either sigma or sigma 2 or sigma 3. They are same. So there exists only a point, and there exists only a point on the Morse plane itself. There is only shear stress exists, and there is no shear strain anywhere in this plane itself. So there are three conditions: sigma 1 not higher than sigma 2, where sigma 2 is higher than sigma 3. We got the three more cycles, and we plot sigma along x-axis and plot tau along y-axis. We get the maximum, minimum value of sigma and tau, and any other value of sigma within the cycle itself, and just by measuring the abscissa and ordinate itself. And then another case is if sigma 1 is equal to sigma 2, but sigma 2 is not equal to sigma 2. And third case is sigma 1 equal to sigma 2, but sigma 2 not equal to sigma 2. Both these cases will have only one axis, because other axes don't have any radius, because they're cancelling each other. And fourth cases is there when sigma 1, sigma 2 and sigma 3 are all equal. There is no circle will created. There is all these stresses, all the points will be on the O sigma axes, and there is no shear stress, and there is no shear plane exist in this particular cycle. Next, what is the Morse stress plane? When points with coordinates sigma tau for all possible planes passing through its point are marked on the sigma tau sigma plane, as in the last page. What is the meaning of this thing? Every point in a plane sigma and tau will have the coordinates either sigma and tau, and you can measure from the axis itself. For the probability, we have a specific scale. All the points may be infinite number, have infinite number of planes. So all the planes have different value of tau and sigma, and these all planes are passing through, just at the beginning I told you, passing through a point P as marked on the tau sigma plane itself. As in figure last page, the points are bound by three Morse cycles. This is put like this. So we have maximum 3 Morse cycle, minimum no Morse cycle, 1 each, and 3 Morse cycle. So we can prove it like this. What will be the coordinate frame? Choose the coordinate frame of reference. We again go to the original one, that is P, X, Y, Z. P is the origin. Origin here is not shown by the term O, but by the term P itself. P means P means the origin itself, Px. Sorry, Px, just a second. Now, choose the coordinate frame of reference P, X, Y, Z. That is, P is the origin, Px, Py, Pz, such that the axes are along with principal axis. We have initially started like this. Along the principal axis lies this plane, and on any plane with normal ends, we are again imagining a plane going through the point P. Each plane is supposed to have a normal, which is at 90-degree angle with the plane itself. We are considering any plane through the normal end. This point we have to very clear in your mind. A plane passing through a point have a normal end, and any point may have infinite number of planes and infinite number of normals acting over its respective planes. This following theory is applicable everywhere in the stress solutions, stress analysis. Well, now what we have any plane with a normal end, we have a resultant stress vector Tn acting over along the normal stress tau sigma and shear stress tau. So we have a resultant stress over acting over the plane which may run parallel to the normal end. This is the conception, not along the normal end, but parallel. So it has a normal stress sigma, also it had shear stress tau. So the normal stress tau are such that Tx sigma nx, Ty or the component of the resultant T along x-axis, Tx